Okay, so geometric series test and the p-series test are very similar in the sense that their conclusions about r and p are opposites of each other. So geometric series test converges when the absolute value of r is between 0 and 1, whereas and diverges when the absolute value of r is greater than or equal to 1. P-series converges when p is greater than 1 and p is less than or equal to 1. Note that they both diverge when the value equals 1. So that is actually similar. They both diverge when the value equals 1. But this can be confusing, and I'll give you a couple of examples here and help you kind of understand why they have the conclusions that they do. So let's look at two geometric series. So let's say a sub n is 1 over 3 to the n, and let's say a sub n is 3 to the n. And then over here, let's say a sub n is 1 over k to the 3, or I guess we should use n. And let's say a sub n is 1 over n to the 1/3. Okay, so here for the geometric series, r is equal to 1/3, so this converges. And here r is equal to 3, so this diverges. Here p is equal to 3, so this converges. And here p is equal to 1/3, and this diverges. So why does this make sense? Well, let's think about what happens for this first series here. If we add up this series, this would be 1/3. If we start at 1, it would be 1/3 plus 1 over 3 squared plus 1 over, so we'll just actually write it out. 1 over 9 plus 1 over 27 plus ... Whereas this guy is 3 plus 9 plus 27 plus ... So it's pretty obvious that this guy is going to diverge because you keep adding up those bigger numbers and that's just going to keep getting bigger and bigger and bigger. There's no way that sum is going to approach a value. But these numbers are getting smaller and smaller and smaller and pretty significantly smaller. 1 over 27th is very significantly smaller than 1/9. So their values are approaching 0, and so if we keep adding on these really teeny tiny values, it still will approach a number. And in fact, you know that it is 1 over 1 minus 1/3, which will be 1 over 2/3 or 3/2. So this will end up being equal to 3/2 if you keep adding all of those numbers up infinitely. Okay? So that kind of makes sense why it converges when r is less than 1. Because if it's bigger than 1, the numbers are clearly going to get bigger as you raise them to a power. So what happens with the p-series? Well, let's look at this guy, what this happens. If we start at 1, that'll be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed, ... And then if we look at this one, we'll have 1 over 1 plus 1 over the cube root of 2 plus 1 over the cube root of 3 plus 1 over the cube root of 4 plus 1 over the cube root of 5. Now here, both of these are approaching 0, the sequences, right? The fractions here are getting closer and closer to 0, and the fractions here are getting closer and closer to 0. So one might think they both converge. But if you look at these values here in the denominator, the cube root of 4 compared to the cube root of 9, these values are getting, the fractions will go to 0, but the values in the bottom are getting bigger much slower than the values in the denominator here. These are getting huge, right? 5 cubed is a giant number. 4 cubed is a giant number. The cube root of 4 is bigger than this, right? So they're getting bigger, but not fast enough to be able to converge, right? So these are very clearly getting smaller and smaller and smaller, closer to 0, so tiny that if you keep adding them together, you'll go to 0. But when you take a root, it's not growing quite as fast. It's still growing, so the sequence will converge to 0. But the series, the values are not getting small enough faster that they will converge for the series when you add them up. So that's just a helpful tip for understanding the difference and why the values are what they are.